All right, we just went over the the midterm exam. I've posted homework 11. That's due on Wednesday. And when I was looking over that assignment, I think you've done already everything you need to know. You've seen except for stochastic. And so what I've done is I've flipped the topic of today's class and what was going to be on Monday. So on Monday we'll talk about HEC HMS, and today we're going to do this stochastic modeling, just so you have seen this a little bit sooner, and for those who want to get an early start on the assignment. So the assignment's posted now, and what we're going to do today, let me give you a handout that shows the watershed we're going to work with. And really, I think just to cover ground as quickly as possible, what I'll suggest is that you watch me, but if you're not yet really comfortable with WMS, maybe just watch rather than try and also do it yourself, because I'm going to have to move quickly in order to get the watershed delineated and set up and still have time left over for us to do the stochastic part. So in other words, if you're a WMS ninja, follow along. But if you're not, then just watch. And then maybe you can practice it using the video later. All right, so this is a watershed that I'm familiar with because I run through here about every week. It's very unusual. If you look at the parallel streams, that's not common in this area. And so I always have a pretty easy time finding this watershed because it has these parallel haulers. You know, here you can see 1, 2, 3, 4 that are parallel. So it's very unusual. So we're going to look at Big Cabell Creek, and I'm just going to go through the process of delineating the watershed, calculating the curve number from soil type and land use data, and then we're going to talk about uncertainty, because that's kind of the ugly little secret in hydrology. And fortunately, WMS gives us some tools to efficiently deal with the effects of uncertainty. But what I mean by ugly little secret is, you know, engineers, we like for our work to be really quantitative and definitive and defensible and repeatable. But sometimes hydrology is just built on guesses. Hopefully they're good guesses, but we have to, for example, make extrapolations with rainfall data. And that can be uncomfortable when we're saying that, you know, we're going to build some infrastructure based on our best guess of precipitation. People don't like the sound of guess. So let's take a look at Big Cabell Creek. All right, so just starting with the wizard, I'll try and find this site on the map. I see those parallel, see them? They stick out like a sore thumb. I can just spot them in the entire county map. Here they are. Okay. So here's our project area. We're going to use the web services, and like usual, I need the elevation data to delineate the watershed boundaries, national land cover to get the land use, and Surgo for our soil type. So we tell it to begin downloading. 15-meter resolution for the DEM will be plenty of resolution. 20-meter standard resolution for the land use, and then it gets the soil type as shape files, which is kind of infinitely precise, except for the fact that soil type classifications are based on slopes and elevation data in a lot of cases. You probably already noticed that, you know, it's not completely independent what the soil type looks like compared to the elevation map. By the way, WMS downloaded an adjacent county, I think north of Cabell. Is that Mason County?
Yeah, I think so.
All right, so we don't need Mason County. You can see that's outside of our area, so I'm just going to delete that. And before I forget, I'll right-click and join the NRCS data for the soil type and fill the blank values with D. I don't know if there will be any blank values, but if there are, I want to be conservative in that. I'll go back to the wizard and run Topaz and choose our outlet. So compute Topaz. It does that quick enough. All right. And let me switch off the land use grid and the soil type. I don't need this heat map either. All right, so I kind of know just by the shapes, rather than turning on the maps and waiting for that, I'm just going to drop my outlet location right here. And that's where I know it needs to be. And delineate the watershed. Oh, shoot. Look at that. Here I was getting sloppy. All right, I got to throw it out and start from scratch. All right. Oh, all right. So it looks like what I was missing. Hopefully that's it. All right. Download the data. If I get it again, then that'll just really be a bummer. I'll just have to actually zoom out rather than just panning. 3, my ninja status is revoked, right? You got white belt.
He's at least yellow. Come on, white belt. Starting belt.
That's not far from wrong. All right, Topaz. I use WMS a grand total of like 4 days a year, so I'm hardly an expert at this thing. Let me switch off the soil type and all this. All right. Okay. Oh, hopefully that was on the flow accumulation cell. I'm just really speeding because I want to spend most of the time on the stochastic model. Oh, what a relief. Not a white belt. All right. All right, so let's see. I need to join NRCS again because I had started over, right? Okay. Select the, I need to create my soil type coverage. And select the data and put it into the soil type coverage. Okay, so I've selected the polygons out of the GIS data, and with them selected, now I can map them into the soil type coverage, making sure that it recognizes the hydrologic soil group as the SCS soil type, which it does. Okay, now that those are copied into the soil type coverage, I can turn off the shape file, and they're in the soil type coverage whether or not I've got them visualized, so I can just turn that off. Now I'll go into the hydrologic modeling module and use the calculator to compute GIS attributes. I need to import, hopefully I've got the text file saved somewhere. Let's see, what folder would I have had that in? All right, and it'll calculate the curve number. I think it's going to be, what is it, 60 something?
I got like a really low
68. Yeah, if we look at this, check out grasslands, soil type A. There's just a tiny little 1/4 acre of grasslands on type A soil that has a curve number of 30. But that doesn't have much of an effect when the majority of the watershed you can see is type C soils. Even though this has a lot of, it's mostly undeveloped or agricultural. Okay. So I'm going to just quickly do a HEC1 model. Precipitation, basin average, and I'm going to get precipitation from Webb. That just uses the coordinates of the site, and I'm going to do a 10-year storm. When I click Get Data, I want to write down, because we're going to be referring to it later, the upper value and the lower value. So upper value for the precipitation 10-year storm is 3.842 inches. And then the mean, meaning like our best guess of the 10-year precipitation depth, is 3.61. And then the lower is 3.39 inches. Okay. Now, that's some uncertainty in our precipitation. Let me just very briefly point out some things that would make us feel bad about our curve numbers. Okay, get precipitation data, 10-year, get data, okay. So it's copied that in, and I have to define the series because I know the depth, but not yet the timing of it. So now I'm telling it type 2, 24-hour, and my precipitation is defined. Now here in the loss method, we can see it's assuming that curve number of 68.2, which for now is our best guess, but how good is that really? Like if you look at the soil type coverage, it's just basically these soil type polygons are really derived from elevation contours. And so they didn't send someone out into this watershed with a shovel to actually test the soil. I don't think that any of these soil polygons were actually measured by someone from USDA. Instead, they looked at maybe some adjacent watersheds and they said, well, typically when you've got a certain slope, that means that a certain type of soil is there. And so they know that if the soil is resisting erosion here, like it did somewhere else, maybe that tells them what the soil type is at this location, simply because it's at a given elevation, at a certain slope. And so they kind of are making inferences about what the soil is, but not direct measurements. And so the likelihood is that there's some error, that if we actually went out into the field and took a sample of the soil, maybe we wouldn't see that that quarter acre of type A soil is really type A soil. We might find it's something else, or maybe it's more than a quarter acre. So I just wanted to point out that there's not really as much resolution in our watershed as we think when it comes to the soil type. I mean, it's the best we've got, so we're going to go with it. And it's repeatable because it's a government database, and the polygons are always going to import in the same location. No matter how many times we do it, or no matter whether you open the polygon or I open the polygon, it's not a judgment call where it is, but it's not based on physical measurement. So there's some uncertainty with the curve number. So our curve number, let me just open up the thing again here, 68.2. So CN 68.2. And I kind of wish I had that report still open, but I've closed that. What if it's as low as 63? So if we went 5 units below that, or what if it's as high as 73? I mean, it's possible that it could be drastically lower or drastically higher. So we're going to test the sensitivity of a HEC1 model to changes in precipitation and to changes in curve number. We just want to look at the spectrum. Like what kind of flow rates are we going to see if it turns out to be the lower precipitation and the lower curve number? Or what if it's the higher precipitation and the higher curve number? So I still need to use the basin data to calculate the lag time or curve number. So I'll, like I usually do, use the SES method to calculate the lag time, and that's got the watershed length from the elevation layer, the SCS curve number that's just been calculated, and the slope, which also comes from the DEM. So it's estimating 0.626 hours for the lag time. Now, this is important. We're going to be playing around with the curve number, but it is not going to change the curve number here. So although we are going to be changing the curve number in one place, it's not going to affect every place the curve number is significant. So we're going to be doing like some tinkering today But one thing we won't vary in our tinkering is the lag time. The lag time is going to stay the same. There isn't a stochastic variability way to address lag time changes. So I just wanted to point that out. It's one of the limitations of the Monte Carlo simulation that we'll look at. Okay, so let me just run this. We've set up a HEC1 model, and you've seen these before. You've done them several times. Run simulation, run, okay. And then as soon as we're done, it'll show the hydrograph, which we can pull up. And it's saying that it thinks the peak runoff is going to be 685 CFS. This is just like the baseline. Q equals 685 CFS for precipitation of 3.61 inches and curve number 68.2. All right, so I said, what if we wanted to change the curve number from 63 up to 73? So think about what would you have to do to find the hydrographs for each of those. You'd have to manually, let me delete the hydrograph. You'd have to go in and change the basin characteristics for the loss method and then run it again. You'd have to interact with the menu options a few times, in other words. Let me show you a tool that can make it a little bit more automated, and it's here under the HEC1 menu, Stochastic Modeling. All right, so click on Define Stochastic Model, and it enables some extra parameters here. And at the bottom of the handout, there's a warning. Do you see the warning at the bottom of the handout? It's related to this next step that I'm about to illustrate on the screen. So this is really important. You'll 100% get an error message if you don't change this. So see the default folder that it's saying the base file name should be in? Program files. Most of you, your computer will be set up so that there's like a write protection in your program files folder, and it won't be able to actually save the model there. So by the way, I haven't yet saved my project. I better do that. Save. I'm going to do it stochastic here. So I've saved my project now. Now back to this stochastic. I need to change the location. I don't know why by default it thinks it ought to be in the program files, but if you change it to that same directory that you're doing your work in, like close to the root of the hard drive, so now I've put it in this folder temp and stochastic. Okay, so I just changed the file name. So now when I execute this model, it's not trying to read and write to the program files folder, which is protected. It's to a folder that I can read and write to without getting an error message. Okay, so down here at the bottom, add variable. What I want to do is add the variable, and you'll notice it says curve number. So I can change the curve number that it's going to run simulations on. And this key of -1 is a reminder that we have to go back into the menu options on HEC1 and tell it that the curve number is -1. And when the program sees -1 for the curve number, it's going to know to look at this stochastic section for the actual curve numbers that it should utilize. So it's kind of just like a substitute trigger flag. Okay, so I'm going to, by default, if you scroll to the side, 100 simulations, no, we don't want to do 100. Let's start with 10. Okay, so 10 simulations, and so if you scroll to the side, I don't think it's, there we go, 10. So it knows right now that I want a normal distribution, that the minimum curve number should be 60, the maximum should be 70, the starting middle point is 75, and its standard deviation is 10. So it randomly selected these curve numbers from these parameters of the midpoint, the minimum, maximum, and standard deviation. I want to just at first find out the effect of certain curve numbers. And so I'm going to overwrite its automatically generated curve numbers. Let me just turn this off so that it's not using the normal distribution. It's blank now because I've clicked this box, and I can just type in, I want it to be curve number 63, then 64, 65, and so on. Okay, so I've got 63 through 72. I guess if I wanted 73 as well, I have to add one more. Oh, and it clears them all. That's clumsy. 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73. All right. So it's going to do a HEC1 simulation for each one of these different curve numbers. Okay, click OK. Now I have to go back into the HEC1 model and put in that curve number trigger in the loss method. I have to put in -1 for the curve number. And so when the program sees -1, then it will look at this other file for which curve number it ought to use. But the curve number that goes into the unit hydrograph method, we're not going to change that. It's going to stick with the same lag time that was defined previously. So it'll have the same lag time even though it's got a different curve number. Okay, so now if I do run stochastic model with any luck, and I click OK, and it's going to go through it over and over 11 times. You can see at the top, simulation 2, simulation 3, simulation 4. Depending on your processor speed, it may go faster than mine. Simulation 7, 8, 9, 10. I need to go through 11, and then it'll automatically write all of the hydrographs to here. And now we can see the envelope of possible flow rates. So it started off with this first simulation was curve number 63. So with a curve number of 63, it was saying that the peak flow rate is 435 CFS. So curve number 63, then solution 2, it said 477. So that was the curve number of 64. Here's the curve number of 65. 523 is the peak. So this is crazy, right? Look, from the curve number of 63 yielded a flow rate of 436 CFS. And then the curve number of 73, which was our last one, said 953 CFS. I mean, that's doubling. The peak flow rate is twice as high for a curve number of 63 compared to a curve number of 73 compared to 63. So we really have a sense for how high the stakes are when it comes to our uncertainty. Now, so how big is the range? Probably the range of 63 to 73 is exaggerating our uncertainty here. My guess is that maybe the window of possibilities is probably narrower than that, but it's not so bad as this. But I mean, if it really matters, like if you're designing a critical piece of infrastructure rather than just, a culvert under someone's driveway where the stakes are a little bit lower. I mean, if you're designing something that absolutely cannot fail, then either you need to go into the field and test the soil and try and confirm some of the polygons and, is it type A soil where it says it's type A soil? Is it type C soil where it says it is? So you either go do that physical validation, send a geologist out or a geotechnical engineer, or just assume the worst case. Take its estimation and then go with the upper window of what may be possible. Say, we calculated curve number 68, but we're going to go with 73 because we don't mess around and we want to just be prepared for everything. So that is how we do a stochastic model for curve number. Any questions so far about this part of it? Okay, now I know the steps are confusing, so let me just refresh your memory what we did. I'm going to delete these hydrographs. So let's just think we just did a normal HEC1 model. Then you open this up and you have to put in the -1 trigger into whatever it is you're going to be doing the stochastic simulation on. So we just did it on curve number, and so the -1 was in this curve number field. Let me put it back to 68.2, and now I'm going to do the stochastic variability on the precipitation, because right now it says this precipitation is 3.61, but I want to do this range that we'd looked at before. So I'm going to put in the trigger of -1. And so now, if I go into HEC1 stochastic modeling, I'm going to delete this row that was the curve number simulation. I'll delete that variable and add instead in the drop-down box precipitation. Okay, so it's giving me this reminder that I need to use -1, and it automatically, it thinks the precipitation is going to be 75. That seems a bit high for the depth. I'll just manually, maybe this time I will use the normal distribution. Okay, the starting point though, it's obviously not 75 inches, it's 3.61 inches. The minimum would be our lower of 3.39 inches. The maximum should be 3.842 inches. And standard deviation. So think about a bell curve. We've got a bell curve, and our midpoint is at 3.61. The upper edge is 3.842. The lower is 3.39. So the standard deviation is supposed to be how far away is it to where you've got 67% of the area under the curve. So it's not good. It would be the difference between these two, but not quite as much as that. So I'm just going to say 0.15 for the size of our standard deviation, and then normally distributed is fine. I don't know if my mouse just died or if the computer just locked up. Oh, here we go. Wait. Okay. So you can see it's randomly generated these rainfall depths with a normal distribution. So it's clustered around the midpoint of 3.61. But let's see, what's the largest of these? I wish it was possible to make this window a bit wider, but it's not. So here's a 3.8, a 3.39. So we've got, from the minimum to the maximum, but most of the runs are closer to that midpoint. And so if I say OK, and then I run this simulation again, run stochastic model, OK, it'll do it 11 times. By default, it says 100 simulations. So you'd maybe want to do that before you go make yourself something to eat, but you don't want to just sit and wait and stare at it as it goes through 100 simulations, because it'll just take too long. We won't do 100 today. Okay, so it's done with the 100. It's going to read the solution, and then here's the range of flow rates that we see with, so this was just curve number variation only. Okay, so the flow rate range that we see now for the simulation we just did, what's our largest flow rate? This one. They're not in order like they were with the other one. So 798. 798 CFS, as low as 578. So it seems like our model is less sensitive to variation in precipitation depth than it was for curve number, at least on the scale that we allowed the variables to change. But where things get really interesting is when you combine the two. When you say, you know, we don't just have uncertainty in precipitation or curve number, we've got uncertainty with both. And so let me throw this away. By the way, remember that if you want to, you can export this data. Right-click, export/print, text/data, file. You identify the location you want the file to be. I'd call this export data.txt. And then what we say is data and labels, comma delimited, table, I guess that removes the comma option, table points/subsets, and then you could export it, and then you could open up that in a spreadsheet and make your own curves. But okay, so my greater point though, if I delete these old hydrographs, is that we can have some variability in both precipitation and curve number. So let me put the -1 trigger into both. So it still has the -1 trigger in precipitation, and it's still, and I'm going to put again the -1 trigger into the curve number. So it's going to look elsewhere. It knows that that's not a real curve number or depth. And so here in the stochastic modeling parameters, I'm going to add, well, let me delete this. Well, I guess I'll leave the precipitation as it is. And I'm going to add the curve number. And then I'm going to put in, this time I'm going to do 100 simulations. I'm not actually going to run them, but I'm just going to put in 100 simulations to show you the idea there. So the precipitation is using the midpoint of 3.61, maximum minimum, and the standard deviation. So it has just randomly generated a bunch of different precipitation values. And then it does the same thing with the curve number. So let's say I want my curve number midpoint to be 68.2, a minimum of 63, a maximum of 73, and then the standard deviation, if I'm just thinking about that bell-shaped curve, you know, how wide is my standard deviation likely to be? If my minimum and maximum is 5, I'm going to say 3 for the standard deviation of the curve number. All right, so now it's generating lots of combinations. So 3.6 is the precip and 67 for the curve number. And if you have 100 runs, you're probably going to get all of your quadrants satisfied. And this is a 2x2 matrix where we have precip and curve number. So you may have a high curve number and a low curve number, high precipitation and low precipitation. And of course, it's not just binary. It's not just high and low, but it's some values that are really high, some values that are really low, and some of them that are in between. But we're going to have, if we've got 100 simulations, there's going to be something in that envelope that is high precipitation and high curve number, and it's going to give us a really large runoff. So I'm going to say OK, and I'm actually going to go ahead and run it. And we'll let it run, and I can abort. But we've got 4 minutes, so let's just see how many of these simulations we can get it to do in the 4 minutes that are remaining. And then we'll pull up the hydrographs just to see how much wider the range of flow rates is. Because my suspicion is that we're probably going to see a flow rate higher than 953. Because the 953 was high curve number but normal precipitation, like in the midpoint of our precipitation range. But if you combine the high precipitation and the high curve number, we'll see well over 1,000 CFS, is my suspicion. So we're just on simulation 23, 24. Any questions while the computer chugs along?
So
So it only is going to run 100 simulations, or does it do, like, it has 100 curve number values and 100 precipitation values? Will it do each one of those curve number values with each one of those precipitation values and get like 10,000 simulations?
No, it's just doing 100.
Okay.
Yeah, so you can see in advance what the combinations are by scrolling to the side.
So it only does those combinations?
Uh-huh.
Okay.
Yeah, those are the specific values that it's doing. So if you wanted the true 100 by 100, then yeah, you'd need to put in 10,000, but I'm not convinced that it would even be able to open up the hydrographs, 10,000 hydrographs.
Yeah.
It'd probably crash. It may write the text file though, because you know all of the things that it creates as it continues to go. Let me just point out that a lot of the files that it's making are just text files that you could open up in a text editor, like this out and the soul. Here's the results of our solutions, right? If I open up Notepad, even though that's a file extension you're not accustomed to seeing, .out and .sol, solution it means, I think you could open up the files in the text editor. Let's see, stochastic, all document types. Yeah, so let me open up this solution file. So these are the runoff parameters. That was the solution, and if I open up the output, OUT, oh, look at that. That's a nice little report. That has the runoff. Yeah, so I mean, the data's there, but what WMS does is, okay, what are we on? Run's finished. All right. So let me open up the hydrograph. Okay, so here's all 100 of them. Looks like I was wrong. I thought that we'd have a precipitation that was above the 953, but we didn't. And I don't know if that's just because of the the random nature of maybe we never got that high precipitation in the same combination as the high curve number. But if we look at the envelope of possibilities, it's saying that the largest one of them is 931.
I did 10 runs and got 968.
968? Well, hopefully that gives you an idea of the functionality. The assignment is posted online if you want to get a start on that. We're all going to use the same watershed for this one, rather than pick your own watershed that you've done in the past. So that's available now, and sorry that I had to rush through it, but the recording will be on YouTube, so if you miss a particular step, then you can refer back to the video for that.